This is the notes page for complex numbers, but we want to do a little review first. So, do you remember how to solve x squared plus 4x equals 21? It's quadratic, so you have to set it equal to 0 100% of the time. Then we want to see if it factors. So the factors are 21, 1 and 21, 3 and 7, and we want to see which one of those factors subtract to be 4. That would be 3 and 7. So x plus 7x minus 3 equals 0 is the factored form. You want a positive 4, so the 7's positive. Then you set each factor equal to 0, and you get x is equal to negative 7 or x is equal to 3. Alright, now what we want to do is check those solutions by graphing this function, which is x squared plus 4x minus 21. Okay, so I've graphed it. F of x equals x squared plus 4x minus 21. This is the function, the related function that's related to this quadratic equation where y is equal to 0. And remember, y equals 0 gives us the x-intercepts. So if I click on these x-intercepts, I get the solutions, negative 7 and 3. So there's a relationship between the solutions to the quadratic equation and the x-intercepts of the quadratic function. So I'll just sketch that here. So we have negative 7 and 3, and the parabola went through these x-intercepts. Okay, so now what we want to do is graph f of x equals x squared plus x squared plus x plus 2. And when I do that, I get this parabola. And so what are the number of x-intercepts? Well, there aren't any, and zeros is another name for x-intercepts. So there are 0 zeros. Okay. The degree of the function, well, that's the exponent that's on the leading term, so that's degree 2. And here's an important fact we'll talk about many times. Since the degree is 2, then we should expect 2 zeros or solutions. Okay, and there are 2 zeros. It's just that they're not real. They are imaginary. Okay, so what is the most basic imaginary, not fake, but imaginary as opposed to real? So the opposite of a real number is an imaginary number. And the most basic imaginary number is the square root of negative 1. There is no real number that exists that is the square root of negative 1. So we're going to call it I as the most basic imaginary number. And imaginary numbers always behave the same way. There's a pattern that repeats every 4 multiples that you need to memorize. So I'll take you through why this works. I is I, or the square root of negative 1. So I is I. I squared is I times I, which is the square root of negative 1 times the square root of negative 1. And when you multiply a square root times itself, you just get negative 1. So I squared is equal to negative 1. Okay, I cubed, we'll leave this square root of negative 1 now and just use these two facts. I cubed is I times I squared. So that would be I times negative 1, which is negative I. So I cubed is negative I. I to the fourth is I squared times I squared. I squared is negative 1, so negative 1 times negative 1 is 1. And that pattern repeats. So with imaginary numbers, you'll either have I, negative 1, negative I, or 1. You'll never have any exponent higher than the understood 1. And if you kept going, I to the fifth is I to the fourth times I. Well, I to the fourth is 1, so I to the fifth is I. I to the sixth is I to the fourth times I squared, which is negative 1. I to the seventh is I to the fourth times I cubed, which is negative I. I to the 8th is I to the 4th times I to the 4th, which is 1 again. I to the 9th is I to the 8th times I. Well, I to the 8th is 1. So you can see the pattern repeats every 4. Okay, so let's say I wanted to figure out what I to the 201 reduces to. Well, I just want to know how many I to the 4ths will fit in that if there's any left over. So if I just do 201 divided by 4, that means that there are 50 I to the 4ths with 0.25 left over. If you convert that to a fraction, that's 1/4. So there's 1 I left over. So I to the 201 is I to the 1, or I. If you had I to the 202, then that would be, again, 50 I to the 4ths over 1 and 1/2 left, or 2/4 left, so that would be I squared, which is -1. If you've had I to the 203 and you divided, 203 divided by 4 is 50.75, and 0.75 is 3/4, so that's I cubed, which is -I. And then if you had I to the 204 and you wanted to figure that out, you just divide by 4 and you get exactly 51 I to the 4ths, so that would be 1. Okay, number 3, a complex number is a number in the form of a plus bi. So this is a really big deal. This is opening up what we know of numbers into a larger set. So before we just had real numbers, and real numbers were either rational or irrational. And rational numbers have integers in them. Rational numbers are anything that can be written as a fraction. Irrational numbers are things like square root of 2, or pi, or e, or square root of 3. And that was it for real numbers. Well, now we're going to add imaginary numbers, which we just learned about. Square root of -1 equals I is the most basic imaginary number. But included in real numbers and imaginary numbers are included in the set called the complex number set. Okay, so when we say solve over the set of complex numbers, what we're really just saying is that your answer might be real or it might be imaginary. So you've been solving over the set of complex numbers. It's just that every one of your answers so far has just been real. Well, now we're accounting for the possibility that you might have some imaginary numbers. So that's what complex number means. So a complex number is always in the form of a plus bi, and the real part goes first, and the pure imaginary part goes second. And like I said, every number is complex. So 5 is a complex number. It's a complex number. You can write it this way: 5 plus 0i. The imaginary part is 0i, and that's 5, because 0 times anything is 0. 2i is also more than just an imaginary number. It's a complex number because you can write that as a plus bi, 0 plus 2i. Its real part is 0. Okay, so don't let that direction mess with you. If I say solve over the set of complex numbers now, it just means that your answers might be imaginary. Okay, they might not. All right, 4, all complex numbers have a conjugate. Okay, so if a plus bi is the complex number that you're given, then a minus bi are conjugates. Notice that it's the imaginary part that has the opposite sign, not the real part. Those are conjugates. So the conjugate of 4 plus 3i is 4 minus 3i. Webassign uses this notation, 5 plus 3i with a bar on it. If you see that, that means what is the conjugate of 5 plus 3i, and that's 5 minus 3i. What would be the conjugate of -5 minus 6i? Remember, the real part stays the same, the imaginary part changes. So those are conjugates of each other. All right, to simplify complex numbers, what you want to do is you want to just treat I like a variable. You want to follow the exponent rules and the like terms rules as if I were an x. However, you're going to want to do this extra bit of reducing. You won't leave I squared alone. You're going to reduce it to -1. Okay, so this gives us practice to just adding and subtracting like terms. 4 plus 3i minus 6 minus 2i. That minus is in front of the parentheses, so it belongs to both terms. So that's 4 plus 3i minus 6 plus 2i. And then we add like terms. So 4 minus 6 is -2, and 3i plus 2i is 5i. And now the calculator won't do, sometimes it'll give you a domain error when you try to raise I to a power, but it will typically add imaginaries together. So if I just put in 4 plus 3i minus parentheses 6 minus 2i and hit enter, it will give you your answer and you check your work. You're going to want to show your work though. Okay, you can also multiply two complex numbers together, and that's just two binomials multiplied together. So you're going to do what you usually do, which is FOIL. So 4 times 5 is 20, and then 4 times -2i is -8i. I call it double distribute. We just distributed the 4. Now we're going to distribute the 3i. That's positive 15i and -6i squared. We have some like terms here, and also I squared is -1. Okay, so -6 times -1 is positive 6. So we have 20 plus 7i, if we add those like terms using our addition and subtraction rules, plus 6, which is 26 plus 7i. Okay, and you could check your work on the calculator, but that's the work you would need to show. Alright, now this is a special one. This is 3 plus 2i times 3 minus 2i. Do you remember what these are called? These are conjugates of each other. So what happens when you multiply two conjugates together? So if you multiply 3 times 3, you get 9, and 3 times -2i, you get -6i, and then 2i times 3, you get positive 6i, and then 2i times -2i is -4i squared. So again, -6i and positive 6i cancel, and again I squared is -1. So -4 times -1 is positive 4, and you get 13. You get real. So I have a shirt that I wear. When you multiply two conjugates together, a plus bi times a minus bi, it's always going to end up being a squared plus b squared. You're going to get real. You're going to lose the imaginary because they cancel, and this I squared becomes -1. So that's interesting that when you multiply two conjugates together, you lose the imaginary part. You just get a real number. Okay, so example 4, I made a little mistake. So this is take 2. The first thing that you want to do is you want to pull out your I, the -5, that's a -1 underneath that radical. So you have to pull out the I. So this would be 3i square root of 5 times 2 plus also I square root of 2. Now you're going to just distribute this 3 times I times square root of 5 to the 2, and this 3i square root of 5 times I square root of 2. So there's multiplication in between all of these things. So you just want to multiply the things that are that look alike together. So 3 times 2 is 6 times I times square root of 5. And then you want to distribute 3, doesn't have any, well, there's a 1 there you could think of. 3 times 1 is 3. And then I times I is I squared. And then the square root of 5 times the square root of 2 is the square root of 10. So now we have I squared. We remember I squared is equal to -1. So that's 6i times the square root of 5. 3 times negative 1 is negative 3 times the square root of 10. And since these aren't like radicals, that's all you can do. And then also you want to make sure if the directions say write it in a plus bi form, we want to move this around since this is my imaginary part and this is my real part, so this could be rewritten as negative 3 times the square root of 10 plus 6i square root of 5. So there we go. Alright, it's very important for you to do that first because if you don't pull the I out, you'll lose a negative. So if I did this wrong, I might say, oh, that's the square root of 8, but it's not. So you have to pull an I out first. So that's I square root of 1. Obviously, that's I, right? Hopefully you see that. But I pulled the I out, and I know that's I, but then what you would do is you would do I times I, which is I squared times square root of 8. But I squared is negative 1, so that's negative square root of 8. See, if you multiply those two together first, you think the answer is positive square root of 8, but it's really not. It's negative square root of 8. All right, and then you have to simplify that radical, which is 4 times 2. So this becomes negative 2 square root of 2. Okay, so you have to pull an I out first. That's what you get from those two examples. Okay, and then back to when you have I, you just multiply 2i times negative 8i really just means 2 times I times negative 8 times I. So you can match up the two things that are together, that are alike. 2 times negative 8 is negative 16, and I times I is I squared, but I squared is negative 1, so negative 16 times negative 1 is 16. Okay, next example. We have a couple of factors. I'm going to call them factors. Do you see the x? That makes that a factor. Okay, anything with an x minus in it, and this would be x minus a negative 4i and x minus a positive 4i. Those are factors, and you can multiply those two factors together just like you would. You would double distribute or FOIL. So you have x times x, that's x squared, and then x times negative 4i is negative 4ix. And then 4i times x is positive 4ix. And negative 4i times positive 4i times negative 4i is negative 16i squared. Okay, what happens here and here is they cancel to 0. They're opposites. And again, I squared is negative 1. So negative 16 times negative 1 is positive 16. And so you're left with x squared plus 16. So just notice what we've got here. This is a quadratic. It's not a difference of two squares, so it doesn't factor into x plus 4i, but it doesn't factor into x plus 4 x minus 4, but it does factor into x plus 4i times x minus 4i. So you can factor over the set of complex numbers as well. We'll get to that, but the skill work, hopefully you understand. Okay, do you remember what this notation means? This is 5 plus 3i times the conjugate of 5 plus 3i, which is 5 minus 3i. So you can do this the long way. FOIL it out. That's 25 minus 15i plus 15i minus 9i squared. And they cancel. And I squared is negative 1. So negative 9 times negative 1 is positive 9. And you get 34. And again, we talked about that. When you multiply a complex number times its conjugate, you get a squared plus b squared. You get real. Okay, so now we're ready to go back to solving quadratics. Okay, so x squared plus x equals negative 2. If we want to solve that, first thing we want to do is set it equal to 0 because it's quadratic. So x squared plus x plus 2 equals 0, and you might remember that that's one of the functions that we graphed, and when we graphed f of x equals x squared plus x plus 2, we got that. And you can see it does not cross the x-axis. It's kind of hard to see. So how would we solve that? We can use the quadratic formula, right? So x equals negative b, which would be negative 1, plus or minus the square root of 1 squared minus 4 times a, which is 1, times c, which is 2. All of that over 2 times 1. So x equals negative 1 plus or minus the square root of 1 minus 8 is negative 7 over 2. And x equals negative 1 plus or minus, you have to pull an I out with a negative under a radical, so that's I root 7 over 2. So we said that it did not have any zeros, it didn't have any x-intercepts, it didn't cross the x-axis, but it had a degree 2, and so since the degree is 2, we should expect 2 zeros or solutions. So in fact there are 2 zeros, it's just that they're imaginary. So these don't show up on the graph because the graph is only real numbers, but these are the solutions to this quadratic. These are complex solutions. They are imaginary. Okay, so now we can say solve this, and before today you would get here, and if you got here you would say no solution, no real solution. But now you would have to say these are the solutions. Okay. Now if it were a word problem you would still say no real solution because word problems are only real numbers. Okay, and so the last thing is I've got this really complicated looking pair of factors. It's the product of x minus parentheses 2 minus 5i, this complex number, times x minus parentheses 2 plus 5i. And these two complex numbers, notice that they're conjugates. And I just wanted to take you through a shortcut and a really cool way to simplify this that's going to help you in future lessons. Okay, so what you can do is first you want to distribute the negative. So that would be x minus 2 plus 5i times x minus 2 minus 5i. So distribute the negative. Alright, then what we're going to do is something we've never done before. We start to get these clever little tricks, and that is we're going to regroup. So we're going to just group the x minus 2 together. Like that. That doesn't change anything. So that's legal. Okay, then what we want to do is it starts to get a little tricky conceptually, but you can treat that as one thing. So that's A, and that's the same thing, so we'll call that A. That's 5i, so we'll call that BI, and that's minus 5i, so we'll call that A minus BI. So we've done that several times. We've done A plus BI times A minus BI several times, and it ends up being A squared plus B squared. But what we're going to do is we're going to just multiply x minus 2 times x minus 2, and we know how to do that because I've been saying square double square a whole lot. So we just regroup, and I'm just showing you that something's afoot here. What can we do? So we're going to multiply x minus 2 times x minus 2. So we're going to square double square. Alright, so that would be x times x is x squared, and then negative 2x, you're going to have two of them, that's negative 4x, so we doubled, and then negative 2 squared is positive 4. So that's the a squared part. And then if you notice that when we multiply the outer and the inner, they just cancel. Okay, so the next thing we're going to do is just multiply bi times negative bi, or 5i times negative 5i. So we did x minus 2 times x minus 2. Now we're going to do 5i times negative 5i, which is negative 25i squared. Okay, so we're going to multiply those two together, and that gives you negative 25i squared is negative 25 times negative 1, so that gives you positive 25. So then you see that you have like terms there. So this ends up being the quadratic x squared minus 4x plus 29. Now we're going to spend a lot of time here, but just notice that this quadratic does have two zeros. And you know what the zeros are? This is 0, 1, that's 0, 2. And if you have the zeros, you can put them into factors. Okay, so that's the trick. Distribute the negative, then regroup, square, double, square, and then so you're multiplying a times a, and then multiply bi times negative bi, and you get the b squared, and the result is a squared plus b squared. Alright, so we can try this again. You see these conjugates here? These are the zeros. These are the factors, and you can multiply them together. Step 1, distribute the negative. Step 2, group those together. And then all you're going to do is multiply those two and multiply those two. Okay. It's a little hard to write down, but hopefully that makes sense. So the way we're going to multiply those two is my little shortcut square double square. That's x squared minus 12x plus 36. And then we're going to multiply negative 2i times positive 2i. That's negative 4i squared, which becomes positive 4. So you get x squared minus 12x plus 40. So this lesson's just a bunch of skill work, so I just added those in there. We'll come back to that at a later date.